Alright, so in this example problem we have a box of treats which has a mass of 0.25 kilograms sitting on a horizontal surface. And we're given both the static at 0.4 and kinetic 0.2, the coefficients of kinetic friction. And we have a guinea pig that is going to first apply a force of 0.5 newtons, and we want to know what the force due to friction on the box is. And then we want to know what minimum force must the guinea pig apply to start the box moving. And then we want to know what force must the guinea pig apply to keep the box in motion at a constant velocity. And then finally in part D, we want to know what force must the guinea pig apply to the box to move it with a net acceleration of 0.1 meters per second squared. Alright, so to start this problem off, we have to remember that the force due to static friction is less than or equal to the coefficient of static friction times the force normal. So it's an inequality. And until the guinea pig pushes with a force that is equal to or above the force due to static friction maximum, the object is not going to move. Up until that point, the force applied and the force of friction are going to equal each other. So the first thing I'm doing over here is, of course, I'm drawing my free body diagram because we have a force of friction opposing the force applied by the guinea pig. We have a force normal because it's on a horizontal surface, and then we have the weight of the box of the treats. In this case, if we sum forces in the y direction, the force of gravity is going to equal the force normal. So subbing in the idea that the force of friction static is less than or equal to the coefficient of static friction times the force normal, I'm going to take my coefficient of static friction, and remember weight is m times g. So we're going to take my mass here times our gravitational field strength of 9.8 meters per second squared. So the force due to friction static is less than or equal to 0.98 newtons. So until the guinea pig pushes with 0.98 newtons, the force applied by the guinea pig is going to equal the force due to friction. And that's what I'm expressing here in part A, because we were asked in part A, what happens if the guinea pig pushes with 0.5 newtons? So I'm summing forces in my x, so force applied minus force of friction is going to equal 0. And I know it's going to equal 0 because 0.5 newtons is less than 0.98 newtons, so the box will not move. So force applied is going to equal force of friction, or 0.5 newtons. I've sort of already answered part B in the process of doing this. What force is the minimum you need in order to start a motion? And that's going to be that 0.98 newtons, that maximum static friction. You need to apply with at least that much force to get it in motion. In part C, we want to know what force the guinea pig must apply to keep the box in motion at constant velocity. Alright, so now the box is moving, so we've changed what type of friction we're dealing with. We switched from static to kinetic, which is why here I'm recalculating my force due to friction. So force due to friction kinetic equals the kinetic friction times the force normal. So I'm going to take 0.2 times the mass times our gravitational field strength to get 0.49 newtons. I've now summed forces in the x direction again, force applied minus force of friction. It's still going to equal 0. This time not because the system is at rest, because the system is moving with constant velocity. Constant velocity means 0 acceleration. Mass times 0 is still 0. So the guinea pig needs to continuously push with 0.49 newtons to keep the box in motion with a constant velocity. If now the guinea pig wants to accelerate the box, so change the velocity, that means the guinea pig should increase the force, and more precisely, because now I have mass times acceleration here, we still have the same friction we're working against, so we're going to take the mass of the box times the acceleration we want to maintain, and we find that it is 0.52 newtons. So this is a little bit of the struggle with friction. Static and kinetic behave differently, and static is not a constant value, kinetic is. So static friction increases with force applied up until the maximum static friction has been reached, and then you can finally apply enough force in order to get the box in motion.